So the last video we looked at this, and now we're kind of taking a culmination of our information together. So I to the first power is just I. I to the second power we recognize as -1 as per the definition. I to the third power we can write as -I, right? I to the fourth power we see is 1. Let's continue on. Let's see what I to the fifth, I to the sixth, I to the seventh, and I to the eighth is. And we'll see if we get a pattern or something that we can do that's predictive. So check it out. I to the fifth power can be written as I to the fourth times I. Rules of exponents. And so I to the fourth is 1 times I tells me that I to the fifth power is simply what? Is simply I. Similarly, I can break down I to the sixth power as I to the fourth times I to the second. We know I to the fourth to be 1, I to the second to be -1. So 1 times -1 is simply -1. So I to the sixth power is equal to -1. I to the seventh, I can write that down as I to the fourth times I to the third. And I to the fourth is just 1, and I to the third is equal to -I, and so 1 times -I is simply that, -I. So I to the seventh is -I. I to the eighth can be written as I to the fourth times I to the fourth. I to the fourth being 1 tells me that this is really just 1 times 1, which is 1. Therefore, I to the eighth is simply 1. As we have right here. So what I'm noticing, and I hope you are too, is that we have a pattern that is emerging. And we're going to use this pattern to answer this question over here. I'm going to shrink this and talk about what the continuation of this pattern looks like. So check this out. If I had, let's continue, if I had like I to the, let's say 9th, then I to the 10th, I to the 11th, and I to the 12th. With similar arguments, right? With a similar argument, I to the 9th can be looked at as I to the 4th times I to the 4th times I. Well, in a sense, we know I to the 4th is just 1, so what we end up with is just I. I to the 10th can be written as I to the 4th times I to the 4th times I squared. Right? We know that this is just 1 times I squared, which is -1. Notice we're getting the same answer over and over again. I to the 4th times I to the 4th times I to the 3rd is I to the 11th. These guys are just 1s. I'm crossing them out, just saying that's 1 times 1. And then we know I to the 3rd is -1. Therefore, we get, -I. Therefore, we get a -I. And finally, I to the 12th is I to the 4th times I to the 4th times I to the 4th, which is 1 times 1 times 1, which is just 1. We can continue doing this forever and ever and creep up to I to the 45th. But what I want you to do is think about, when does this pattern turn? When do we get the rotation? And we get that rotation every fourth. 1, 2, 3, 4, back to I. 1, 2, 3, 4, back to I. 1, 2, 3, 4, back to I. And that will continue, just given the pattern that we see. So what I know is I to the 45th power, right? I can think of it this way as I to the 4th. How many times? Well, I'd have like 10 of these bad boys, right? Or in fact, 11 of these bad boys. I'd have I to the 4th 11 times, right? Because that would give me I to the 44th. I'm going to write it like this. I to the 4th 11 times. So 4 times that 11 times 1 more I to give me I to the 45th. Think about that for a second. And now, if this is I to the 4th, that's just 1 to the 11th power, which is just 1 times I, which is I. So I to the 45th power is I. The way we sometimes do these problems is, since everything happens, every group of 4 we get 1, we can take 45, divide it by 4. When I do that, I get 11 with a remainder of 1. That 1 is the exponent that I think of when I'm raising I to that remainder, that 1. Let's talk about that more when we get to talk in person, if that didn't make much sense. But the answer to this is I. Let's look at a couple more examples. Sometimes we will have equations with imaginary numbers, and don't think that you're going to throw your solution finding ways out the window. We're going to solve these equations with all the algebra that we used to use, even if we were going to get I values. But check it out. The first thing I would do in this situation is I would isolate the x squared as best I can, because I've only have x in one place, x squared here. I'm going to just isolate it by throwing the 48 over to the other side, or by adding a negative 48 to both sides of the equation, and then I get this. And now I'm going to isolate that x squared by dividing both sides by 3. When I do that, I get that x squared is equal to a negative 16. Usually we stop and say, can't take the square root of a negative, so we're done, but now we are in the imaginary realm. So I can take the square root of both sides. Little caveat, keep this in mind. We take the square root of this and the square root of this. Since this is x squared, we have to consider the possibility that this answer is positive and negative, what we're going to get. Plus or minus the square root of negative 16. First thing we do when we simplify a negative under the radical is to pop out the I. So x is equal to plus or minus I root 16. We know that root 16 is simply 4. So x is equal to 4I, well, plus or minus 4I, and that's what we're left with. This 16, when we take the square root of it, the whole number comes in front, and so we get plus or minus 4I. Example 5 has us finding the value of x and y that make the equation true. So here's a little thing. If I told you that a, let me write it in a color you can see, if I told you that a plus bi is equal to some other number, c plus di, the fact is the imaginary parts, that's the I part and the I parts, these guys must be the same, and these guys must be the same. So in instance, if I told you that this was the case, then that means A has to equal C and B has to equal D. All right. So this is the thought that we're thinking about as we approach this problem. So here's this problem. It says that we're going to find the values of x and y that make this situation true, make this equation true. So if I have 2x minus 3 plus all this jazz, y minus 4i, and that's equal to 3 plus 2i, just as I told you the real part must equal itself, the imaginary part must equal itself. So the real part here is this. All of this must equal 3, because this is the part hanging out that's not being multiplied by I. And here, this part that's being multiplied I must equal to this other side that's being multiplied by I. Therefore, this is equal to that. Stop and let that marinate for a second before you continue looking at the video. So think about it. The real part must equal the real part. A must equal C and B must equal D, because the B and D are multiplied by I. So with that, here's my equations that I get. So setting the real parts equal, I get this guy, 2x minus 3 equals 3. What I'm going to do is solve this. Move the 3 over to the other side. I get 2x plus 3 equals 6. Divide both sides by 2. I get that x is equal to 3. Okay, let's do the other one. So now the imaginary part equals the imaginary part. Y minus 4 is equal to 2. And so y is equal to, I'm being a little bit quick here, positive 6. That's if I add 4 to both sides, I get a positive 6, and that's it. And therefore, my answer is x equals 3 and y equals 6. So that example wasn't too bad. Let's look at example 6. We're going to add and subtract complex numbers. Now, the cool thing about adding and subtracting complex numbers is that it's easy. In this case, we're going to treat I like a variable, and we're just going to join like terms together. 6 plus 1 is going to give me 7, and then minus 4i plus a positive 3i, that's literally what we're doing, is going to end up giving me a minus I, right? A minus 1i, and that's it. So the trick to this is treating it just like you would if you had 6 minus 4x plus 1 plus 3x. Exactly the same idea. You're going to treat I like it's a variable. Let's do the second part B. Part B is very much like the other parts, except we're going to distribute the negative through. We're going to, in a sense, think of this as a minus 5 and this is a plus 4. So 3 minus 5 gives me a negative 2. That's the real part. And the imaginary part right here is a negative 2i plus a positive 4i, leaves me with a positive 2i. So again, adding and subtracting complex numbers is a cinch if you remember how to add and subtract expressions with variables. Let's look at example 7. So we're going to be multiplying these guys together. Let's check out what's going on. This looks like a J, but these are really I's, and I had to kind of check myself on that just a second ago. So now that we've got that squared away, let's go ahead and check out the problem. In an AC circuit, the voltage E and current I and impedance Z are related by the formula E is equal to I times Z. Find the voltage, that's E, in a circuit when the current is 1 plus 3I amps and the impedance is 7 minus 5I ohms. The fact is, I'm not sure what they're talking about, but I can do the math. And sometimes when you have word problems, you need to be able to distill what's going on to figure out, okay, can I do this? Instead of getting caught up in the details if you find it unfamiliar. So in this case, we're looking at E. We recognize the relationship is E, which we're looking for, is equal to I times Z. I, in this case, they called it the voltage E is what we're looking for. The current is I, and the impedance is Z. So the current, they told us the current in this case is this guy. So that's going to be 1 plus 3I. And the impedance is this in ohms, and we 5I. And so now we're just going to multiply it together. And when I do that, I'm going to FOIL method it, or extended distributive property. So 1 times all of this stuff, and then 3I times all of this stuff, and I'm going to join like terms together. So 1 times 7 is 7, 1 times 5I is a minus 5I. That takes care of the blue part. Next, we're going to do the green part. 3I times 7 is a positive 21I, and then 3I times a minus 5I is going to be a minus 15I squared. Okay, and that takes care of the green part. So now we need to simplify those things. So 7 minus 5I plus 2I is a minus 3I. And this minus 15 times I squared we know is negative 1. So this is a minus 15 times a negative 1, which is actually a positive 15. We're going to join some like terms together. 15 plus 7 gives me 22, and my answer is 22 minus 3I. What did they tell us we were looking for? That's the voltage. And that's the end for us. So that was an example of us multiplying, and this really looks a lot like some of the other multiplication we've done before, FOIL method or multiplying radical expressions. Just like when we were dividing radical expressions, it was more about trying to figure out how to rationalize the denominator. That's what we're going to do. But we want to end up with answers in A plus BI form, meaning we want a real part and an imaginary part. And we can see we can't do that now. So the first thing we're going to do is rationalize the denominator. And I'm going to use the conjugate form, the complex conjugate form, to multiply the top and bottom. And just like last time, we use this fact to multiply conjugate bases. We're going to do the same fact again. Let's look at what happens with our denominator. So we should get this squared minus this squared, which is now my denominator. And if I were to do that math, I get 4 minus 4I times 4I is a 16I squared. I squared in this case is going to make it negative. So I'm going to come down here. 4 minus 16 times a negative 1 is really a positive 1. 4 plus 16 is my denominator. And so my denominator at the end of all this will be 20, right? And the numerator is just, I'm going to multiply 3I times this. Using the distributive property, I get 6I minus 12I squared. I squared is negative 1, so 6I plus 12. Change the order, so I have the real number in the front, like here, and the imaginary number in the back. I get 12 plus 6I. I'm going to reduce this. I can divide a 2 out of each term. 6 plus 3I over 10. And finally, I'm going to split it up so it's in A plus BI form. So then I end up with this, 6 tenths over plus 3I tenths, and then I get this thing here. Let's do this next problem. Again, I need to multiply by a special 1 in order to get rid of the radical, or the I in the denominator. And upon second thought, I over I would be enough, because in the bottom I get 2I squared, which is just a negative 2. And in the numerator, I get 5I plus I squared, which I can then write as negative 1 plus 5I over negative 2, with my final answer simplifying to this. The last thing I'd like you to do is just observe that our assignment is page 274, numbers 19 to 63 odd and 64. Look forward to talking to you soon. Take care.